Imagine waking up to find your front door unlocked. That is the reality of supply chain attacks. A single package update can compromise your entire infrastructure. Recently, the Python package known as LiteLLM faced exactly this situation. Versions 1.82.7 and 1.82.8 on the Python package index were compromised. This incident is not just a glitch. It is a tactical breach of the trust model that software engineers rely on every day. To understand the severity, we must consider how the code executes. Python has a mechanism for initialization files. These files use a specific naming convention ending in .pth. When a package is imported, the Python interpreter automatically runs the code inside these files before any of the main application logic. In this case, attackers injected a malicious file named LiteLLM init.pth. This file contained code designed to harvest sensitive data. It targeted secure shell keys, cloud credentials, and cryptocurrency wallets. The data was encrypted using advanced encryption standard 256 before being exfiltrated to external servers. This means the attacker did not just steal the keys. They stole the keys and locked them away in a digital safe that only they could open. Now consider how this code got into the package in the first place. The breach originated within the project's continuous integration and continuous deployment pipeline. Specifically, the Trivy dependency scanning workflow was compromised. Trivy is a tool used to scan for vulnerabilities. In this instance, the scanner itself was poisoned or manipulated. This allowed the attackers to push malicious code through the upload process as if it were legitimate. It demonstrates that automated security tools are not infallible. If the tool checking the code is compromised, the gatekeeper is asleep. What makes this incident particularly interesting is how it was discovered. Traditional security scanners missed the threat. Instead, an MCP server running in a development environment flagged the anomaly. This stands for Model Context Protocol. It is an interface that allows AI systems to interact with external tools. The AI noticed behavior that did not match the expected profile of the package. This highlights a critical irony. Modern AI-assisted workflows can inadvertently serve as early warning systems for supply chain attacks. The tool designed to help developers code faster also became the detective that caught the thief. For senior engineers, the priority is immediate isolation and rollback. You cannot wait for a patch. You must assume your environment is compromised. The initial step is to revoke all API keys associated with affected environments. This includes database credentials, cloud access tokens, and internal service keys. Treat every key as if it has already been leaked. The subsequent step is to downgrade your dependency management. You must pin the version of LiteLLM to 1.82.6 or earlier. This version predates the breach. Do not update to any new version until the team confirms the supply chain is secure. There is a nuance here regarding Docker images. Users of the official Docker image remain unaffected. This is because the Docker image pins dependencies locally. The containerized environment isolates the dependencies from the host system. This means the attack vector that worked on standard Python installations did not penetrate the containerized environment. However, relying on this isolation is a defensive posture, not a cure. You must still audit the base images to ensure they have not been tampered with upstream. The incident underscores the severe risks of supply chain vulnerabilities. Even popular open-source projects with large user bases are susceptible to rapid credential theft. The attacker successfully impersonated a maintainer to release the malicious versions. This suggests a credential stuffing attack or a compromised maintainer account. The LiteLLM team has responded by rotating all maintainer accounts and revoking credentials across GitHub, Docker, and the Python package index. They have also engaged Mandiant for forensic assistance. This is the correct response. It shows a commitment to transparency and security. However, knowledge gaps persist regarding the full extent of the breach. We are unsure if the fork bomb payload designed to cause RAM exhaustion was a separate phase of the attack or a conflicting initial assessment. Regardless of the specific payload mechanics, the primary attack vector was the unauthorized modification of the package upload process. This requires a shift in how we view trust. We cannot trust a package update simply because it comes from a trusted source. We must verify the integrity of the build process itself. To harden your supply chain post-incident, you need to implement stricter controls. You should enforce signed releases. This ensures that a package has not been altered between the build and the installation. You should also review your continuous integration and continuous deployment pipelines for any single points of failure. If a single compromised credential can push code to production, your security model is too flat. Consider implementing multi-person approval processes for critical updates. This adds a layer of human verification that automated systems cannot bypass. Finally, you must monitor your own environment for signs of the specific behaviors seen in this attack. Monitor for unexpected network connections, unusual memory usage, or background processes that do not match your baseline. The goal is to detect the exfiltration attempt before the damage is complete. This incident is a stark reminder that security is not a feature you add at the end. It is a fundamental property of the system architecture. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.